Hello. So today we will continue our discussion with the bifurcations in 2D nonlinear systems. So in the previous class, we had seen how the different kinds of bifurcations can occur in when we have a nonlinear 2D system. So as in the 1D case, here also we have saddle node bifurcations, transcritical bifurcations, and also supercritical and subcritical bifurcations. But here we also came across a new kind of bifurcation, which is known as a half bifurcation, which is basically a supercritical bifurcation in the plane polar coordinates, where you can have stable line, a stable spiral giving rise to a stable limit cycle, or you can have a stable limit cycle becoming unstable and giving rise to a larger limit cycle and a stable spiral. Okay, so we had come across those examples, but now we will take a look at a few more examples of bifurcations in 2D systems. For example, we will now see how saddle node bifurcation can give rise to a limit cycle. Okay, so first we start off with this saddle bifurcation limit cycle. So a prototypical example for such a system is basically like this. So to have here also we use plane polar coordinates. R cube minus R to the power 5 and theta dot equal to omega plus VR square. So you recall that this was an example which we had done in the previous class only, where this is the destabilizing term and this is the stabilizing term, and mu is a parameter which is varied. So you see that when uh, mu is below a critical value, mu is below mu critical, you have something like this. So the origin is an unstable fixed point over here, and the R figure looks like that. Okay, so the flow is in this direction. That is a stable fixed point. Sorry, the flow is in this direction. So it will give rise to a stable spiral solutions which turn like that and they come into this fixed point. Now when mu becomes equal to the critical value, then you will have this curve over here. It moves upwards and it just touches the x-axis and it will going down like that. Okay, so you have a half stable fixed point over here. This stable from this direction. So what you get is a half stable limit cycle which circles the stable spiral over here. So this is my half stable limit cycle. What I mean is that all the trajectories which start inside the limit circle, they approach the spiral like this, and all the trajectories that start outwards, they come around the limit cycle. Okay. And finally, when you have when you exceeds this critical value, but is less than 0 at the same time, then there is a saddle node bifurcation which takes place on that side. And what you get is you have an unstable fixed point here and a stable fixed point here. All right. So that basically means that there is an unstable limit cycle. There is a stable spiral point over here, and there is a larger amplitude stable limit cycle which serves the unstable limit cycle. So basically, all trajectories from here get rippled outwards versus stable limit cycle, and all trajectories from here spiral in towards this fixed point, and all trajectories from outside are attracted towards the stable limit cycle. So this was an example of a saddle node bifurcation of limit cycles. Now we come to another kind of bifurcation, which is called a homoclinic bifurcation. This is another new bifurcation which happens in two and higher dimensional systems. So a homoclinic bifurcation is basically given by a prototypical equation of this form. So x dot equal to y and y dot equal to mu y plus x minus x squared plus xy. Or if I write it down in terms of the 2D dynamical system, this implies that x dot is equal to x equal x dot plus x minus x squared. So this is again the example of a nonlinear oscillator where both these terms are nonlinear. So this can give rise to a homoclinic bifurcation. Now, what we mean by homoclinic bifurcation is as follows: like one can analyze the system carefully, but I will just show over here what it basically means. So what happens is that when mu is below a critical value, then the phase portrait of the system, it basically looks like this. For less than some critical value mu c. So in this case, there is a saddle point at the origin, and there is an unstable fixed point over here, and surrounding. So the saddle point has the eigendirections which look like this. So this is the unstable manifold, and this is the stable manifold. Okay, and there is an unstable fixed point over here, and what happens is that there is a stable limit cycle surrounding this unstable fixed point. Okay, so I'll denote the limit cycle by this sort of a line for visualization purposes. So what we see is that all the trajectories which start outside the limit cycle, sorry, stable limit cycle like this. So when mu is less than the critical value, all the trajectories would start from outside the limit cycle, they approach the limit cycle, and all the trajectories from inside also try to approach it like that. Okay, and this is a saddle point, and this is a stable eigendirection, and you will have the stable manifold which looks like this. The stable manifold curves around this point and approaches the saddle like that. Okay, and all the trajectories which start outside the stable manifold, they go like this and go to infinity like that, and similarly on this side. Now when mu increases, the size of the limit cycle over here, it increases gradually, and finally at a critical value of mu, so at mu equal to mu critical, what happens is that the limit cycle, it just about hits the saddle point at the origin. So when that happens, then the trajectories will look like this. You have a trajectory which goes like that and comes back here, and the stable and unstable manifolds like this. So you see now the limit cycle, it does not complete one full turn. I mean, before it comes to completes one full turn, it comes and stops at the origin. And all the trajectories which start from outside the spiral, they spiral towards this fluid cycle. So this is also known as an infinite period bifurcation. Why? Because the limit cycle, it takes infinite time to complete one time period. Okay. And then you will have solutions like this, which go like that. So you see the stable manifold of the, so now what happens is that the stable manifold just about for us, yeah. So the solution specialize the stable manifold, it does not turn around the limit cycle and come to the saddle point, but it comes directly to the saddle point. Just like that. And when mu exceeds the critical value, then the uh, limit cycle and the saddle point, they collide with each other. And when that happens, then the limit cycle basically disappears. Okay. And then the phase portrait will look like this. So at that point, you have the stable saddle point here and the unstable fixed point here. So as it is, you will have the stable and unstable event directions like that. Unstable direction and the stable direction like this. Okay. And basically what happens is that this unstable eigendirection, it goes off like that, and then it goes along like that. And for this, you will have basically solutions that spiral outwards, and it will approach this stable fixed point over here. So this is what the phase portrait looks like. So this is an example of a homoclinic bifurcation. And in this homoclinic bifurcation, the limit cycle basically collides with the saddle point. A stable limit cycle collides with the saddle fixed point, and it disappears. So these were two examples of bifurcations in 2D, which may not be seen in 1D. Also, another important concept is that of quasi-periodic flows. So we saw that a periodic flow, the solution repeats itself after a certain period of time. A quasi-periodic solution occurs when the solution just about tries to repeat itself but does not quite do so. And it can be best seen if you try to visualize a flow on a torus. So in a torus, basically a torus is something which looks like this. So you have one over here, one over here. So this is an example of a torus, right? So in this situation, there are two angles. One is the angle in the azimuthal direction, which is while going around the circumference of the torus like this. So this angle is something which we call as theta 2 direction. And the other angle is while going circling the axis of the torus basically. And this angle we call theta 1. So any trajectory which starts off on the surface of the torus, and we assume that the torus is the radius of the torus does not change. The radius of both this radius as well as this radius, we assume them to be constant. So when we assume the radii of the torus to be a constant, so basically then we are thinking of, so if R1 and R2, we call this radii. If R1 and R2 are constant, then basically the trajectory will stay on the surface of the torus forever. And this essentially happens only when the system is a conservative system, because any dissipation will change the values of R1 and R2. Okay, so this happens only when the system is conservative. So with this, we'll show that quasi-periodic solutions are a characteristic of conservative systems mainly. Okay, now theta 1 belongs to the interval 0 to 2 pi, and so does theta 2. Okay, 0 to 2 pi. So we can somehow, if we consider theta 1 and theta 2 be our dynamical variables, and we consider them to define our phase space, then we can map the phase space on a periodic 2D domain, which goes from 0 to 2 pi. Okay, 0 to 2 pi. Mind you, this is called periodic domain. So suppose a solution, it starts from here at this point and goes like that. When it hits the edge of the domain, it will come back from this end because it's periodic, it can go like that. And then from this end, it will come over here and it can again travel like that. Okay, so this is an example of when the phase space is periodic. Now let us say that the equations of the theta 1 and theta 2 are simply given by theta 1 dot equal to omega 1 and theta 2 dot equal to omega 2. So omega 1 and omega 2 basically denote the frequencies with which these two circumferences are covered, or the angular velocities of the phase point along these two circumferences of radius r1 and r2. Okay, now then the slope of the line, or that basically the slope of a trajectory in the phase space of theta 1 and theta 2 will be given by this line, which is omega 2 by omega 1. Now this can either be a rational number or an irrational number. Okay, so for example, it can be a rational number like example omega 2 omega 1. So 2 is basically a rational number, and this physically implies that by the time one oscillation is completed around the large circle of radius r1, the phase point completes two complete oscillations around the radius r2. Okay, so this basically indicates that if the system starts off from a point theta star, it will again come back to the point theta star, and this basically denotes periodic solutions. Okay, so the thing is that if the ratio omega 2 by omega 1 is rational, it's a rational number, then we have periodic solutions. Okay, now, and this periodic solution can also be mapped onto a square domain easily. Okay. So for example, if say that um, omega 1 by omega 2 is equal to by omega 2 by omega 1 is, yeah, 2 by 3, then the solutions will look like this. Here, this is 1, and this is theta 2. From here it goes to here. It again goes with the constants look like that. From here, it comes back down. Just like that. From here, it comes here. It goes and hits this part. And when it hits this part, then the solution again starts continuing from here. So this is an example of a periodic solution. Okay, and on if you try to map this onto a 3D domain, I mean on the domain of the torus, then the solution will look like a trefoil knot. All right. Now, what happens if it's irrational? If 2 by omega 1 is irrational, then what happens is that the trajectory will never come exactly close in upon itself. Okay, that means it will keep moving in this periodic domain, and we might have two lines moving very close to each other but never quite closing in on themselves. So that is what gives me the quasi-periodic solutions. So this is the condition when the system can exhibit quasi-periodicity. So this basically means that if you have something like this, if you have something like this, then suppose the trajectory starts from somewhere here, it will go up like that, and from here it uh, up there, and from here it again starts to goes up, and then it comes very close but not exactly to this point, and it goes there, and again you have something which goes like that. Okay, so you see that the trajectory sort of seems to repeat itself but does not exactly do that. And then what happens is that each trajectory becomes dense on the torus. That means the trajectory comes arbitrarily close to any given point on the torus, but it does not exactly repeat across that point. Okay, so now we have seen periodic solutions and quasi-periodic solutions. So now we are in a position to actually see what chaotic solutions look like. But as we had seen from the Poincare-Bendixson theorem that chaotic solutions are not possible in a two-dimensional system, the minimum dimensionality that is required for chaotic solutions is 3. So now we look at three-dimensional systems or chaos. So the example of a first equation where chaos was observed formally was this legendary system, which is known as the Lorentz system or the Lorentz equations. So Edward Lorenz, who is also known as by many as the father of chaos, was the person who had seen chaos for the first time in computer simulations of his set of equations. So what he was studying was basically, as he had mentioned in the first lecture of this course, that he had derived this three-dimensional equation from a simplified model of convection rules in the atmosphere. So you know that convection occurs when the fluid from the bottom is heated and then it rises to the top. So if the temperature gradient between the, so here you supply heat and you have the fluid which rises to the top. Okay, so this rising, how fast the fluid will rise from the bottom to the top is controlled by the temperature gradients at the two ends of the system. Okay, T1 and T2. Now, if the temperature gradient, it is proportional to a number which is called the Rayleigh number. Okay, so if the temperature gradient is small, that means this number, the Rayleigh number is also small, then convection does not take place and heat is simply conducted from the bottom to the top while the system is in equilibrium. And When the Rayleigh number becomes large enough, then the system can develop certain instabilities, and then convection begins to take place as the fluid itself starts rising from the bottom to the top. Okay, finally, when this Rayleigh number increases beyond a certain value, the rising fluid it begins to show different kinds of patterns, and finally, beyond a critical value, one observes this chaotic motion of the fluid from the bottom to the top plate. Okay, so this chaotic equation he tried to model convection using the following simplified model, which was later known as the Lorentz equations. So what Lorentz had found was that beyond, and the parameters in the system were basically sigma r and b, all were greater than 0. So what I meant by the Rayleigh number is basically given by the parameter r over here. So this was a measure of the Rayleigh number of the system. Okay, so what Lorentz had seen was that for small values of r, the system had fixed points and limit cycle solutions, as one would expect. Okay, as one we had seen in the 2D systems. But for just beyond the critical value of the uh, parameter r, all the fixed points and limit cycles would become unstable, and yet the solution would never blow up, meaning that the solution would remain in a certain bounded region, yet it will oscillate in such a manner that the oscillation never repeats across itself. So it is neither periodic nor it is blowing up. And so this is what he called chaotic. And what is more interesting was that if he started from, say, two different initial conditions, which were separated by very small values. So for periodic solutions, we saw that the different initial conditions would get attracted to a limit cycle, or if it were non-periodic and it was a stationary flow, it would get attracted to a fixed point, right? But here he observed that the solution starting from two different initial conditions, no matter how small the separation between the initial conditions were, the solutions will deviate after a point of time, and then they would never even look like one another. So the end result will be completely different. And yet the solution will remain bounded within that finite domain. So this very confusing and interesting behavior at that time had gripped the attention of many researchers, and that is how chaos had come into the picture. Okay, so before we see what chaotic solutions look like, first let us analyze this system in more detail. As we had done the analysis of fixed points of 2D systems and 1D systems previously, let us see how the fixed points behave and how they bifurcate. Okay, so you see that the nonlinear terms of this equation are basically contained in the z equation and the y equation. So there are only two nonlinear terms over here. Okay, one interesting thing to note about these equations is the symmetry of the equation. What is the symmetry? That the equations remain invariant if you change x by 2 minus x and minus y. Okay. In other words, the solutions are symmetric about reflection about the z-axis. Okay, so this is one observation that we make. The second observation that we make here is that there is a volume contraction in phase space. Now, what do we mean by this? This is a term which we are coming across for the first time in this course. So suppose you have an arbitrary volume, okay, like this. And this basic volume is basically made up of many different initial conditions, okay. So suppose this is a volume V at time equal to 0. Now the question is, what is the volume at some later time? So as you evolve the system, the initial conditions will evolve as per the right hand side of the equations. For the sake of easiness, we write the equation in the form as x dot equal to f of x, as we had earlier. So the evolution of the volume is basically governed by this term f of x. All right. So if you write to see what the equation of the volume looks like, basically you have to find out what dvdt looks like. So if dvdt rate of change of volume with time. So if this is positive, then the volume swept out by these initial conditions, they would increase with time. And if it is negative, then it means the volume of these initial conditions will basically contract. Okay, so let us take a look at it. One thing which one can make note of is that the initial condition will try to go away like this. So basically, these are the trajectories of the system. They can have various different forms, right? So let us denote n cap as the outward normal from this infinitesimal volume of initial conditions, and then basically the vector f dot n cap, it tells me how the initial condition moves, how a trajectory starting from within this volume moves away from this volume. Basically, it gives me the direction of the trajectory at the boundary of this volume. Okay, so since the volume is basically made up of the initial locations of the trajectories, the change in the surface area enclosing the volume will be determined by this quantity. So then the evolution equation for the volume can be written in terms of this thing. If dt is a small increment in time, then the volume evolves in this manner. All right. So this tells me how the volume increases as a function of time. Hence, we obtain that so S basically gives the surface area enclosed by the volume. So integral the surface. So the left hand side is basically V dot. Surface integral of f dot n cap dA. Now using divergence theorem, this can be written as dot is equal to volume integral of divergence f vector into dv. So this is the evolution equation of the volume of the blob of initial conditions. Now what is the vector f? The vector f is basically given as the right hand side of that equation, which is sigma into pi minus 6 all right. So then divergence of f would basically imply del x of sigma into y minus x plus Okay, and if you solve this basically becomes minus sigma minus 1 and minus b. So then b dot is basically the integral of this quantity over volume b. So this is a constant which is independent of the volume. Therefore, dv dt is nothing but sigma plus 1 plus b into b, or so since both sigma and b are greater than 0, that means that this term is positive in the bracket, and therefore this whole term is a negative quantity. This tells that volume decreases as a function of time, and therefore this proves that there is a contraction of phase space volume. So any given ball of initial conditions in phase space will try to contract, okay, as per this equation. But here is the catch. When I say a ball, I mean it is a volume like this, okay? And when it contracts, it does not necessarily retain its shape. So it can turn into something like this. I'm particularly showing in 2D, or it can turn into something like that. So in 2D, this basically means that the volume of the ball, although it decreases, its surface area might be increasing, or the distance between any 2 points which were initially separated by a particular distance, say r, it might increase to some distance r dashed, where r dash is greater than r. Okay, so although the volume might be decreasing, the distance between any two particular points inside the volume or the surface area of the volume, all these quantities might increase. And this is something that we will see later in a more constructive way, okay, in a more quantitative way. So for the moment, one sees that there cannot be any. So from volume contraction, there are two observations one can make. One is that no quasi-periodic solutions are possible. Why? Because we had seen that quasi-periodic solutions require the system to be conservative. Basically, the volume contraction means that there is some dissipation of energy which is happening in the system, and therefore it cannot exhibit any quasi-periodic solution. The second point is that there is there are no repellers. In other words, there is no repelling fixed point or a repelling closed orbit. Because if that were there, then the solution would be driven infinitely away from them. Okay, so this means that the solutions or any fixed points to exist, the only fixed points possible for this system are either um, stable fixed points or stable or attracting orbits or saddle fixed points. Okay, these are the only fixed points that are possible for the systems, are the stable ones or a saddle one. So later we will see that when this solution is chaotic, then actually the solution comprises a infinite number of unstable orbits. Basically, the solution jumps from one to the other. But we'll come back to that later. First, let us analyze the stability of the fixed points. So I'll just write down the equations again. Okay. So one fixed point is that at the origin. So this is one fixed point of the system. There can be other fixed points which are written as x equal to y, where which implies that x not equal to 0. So if we put x equal to y in the other equations, then we get something like rx minus x minus x square equal to 0. This basically gives me x square plus x into 1 minus. Maybe so this one is since x is not equal to 0, we have and this implies that x are equal to, therefore the other fixed points is. So you see over here that these fixed points do not exist if r is less than 1. They can only exist if r is greater than 1. So r greater than 1. So these fixed points basically correspond to the two overturning roles in the convection system, and there is a pitchfork bifurcation at r equal to 1. At this pitchfork bifurcation, what happens is that origin becomes unstable, and the other fixed points, which we call as extant, or basically they correspond to curves C plus and C minus, and C plus C minus are stable, and these two fixed points are bound. Okay, now if you one can do linear stability about the origin as well, because once when that is being done, then one basically ignores this term in the z equation because we're considering the origin, and then z basically has an exponentially decaying part. Then we can analyze the Jacobian equation in the variables x and y, and you see that when r becomes greater than 1, then the origin becomes a saddle point, and before, when r is less than 1, it was a stable fixed point because all directions are incoming. So basically the some information, and one can actually try and work this out. It is stable node when r is less than 1, and it is a saddle when r is greater than 1. And what about this new fixed point C plus and C minus? So you see that for 1 less than r, some higher value of r equal to rh, you see that both C plus and C minus are stable. Okay. Now, what happens at, and when we say stable, what does the space about those points look like? So in that case, the there is a new sort of fixed point which occurs around the cycle, around the stable fixed point C plus and C minus, and this new fixed point, it appears at some value of r which is below rh, and this is a saddle cycle. So what do we mean by saddle cycle? Basically, we had seen saddle fixed points earlier, which had a stable and unstable manifold. Here, the unstable manifold is not a line, but a circular path. So this basically looks like this. So if this is a stable direction and this is the fixed point C plus, there is a cycle around this point called a saddle cycle. What this basically means is that the flow which starts from inside the saddle cycle approaches C, and the flow which starts away from it, it tries to go away from the cycle. So this is an unstable cycle, and C is a stable fixed point like that. Okay, now what happens is that, and this unstable cycle, it is born at a value of R equal to RC, which is less than RH. So when R lies between RC and RH, then you have this sort of behavior where there is an unstable cycle surrounding the fixed point C plus, and similarly there is an unstable cycle which surrounds the point C minus. And as R increases, the radius of this unstable cycle decreases, and finally at R equal to RH, there is a subcritical of bifurcation. Okay. So when the subcritical half bifurcation happens, then the unstable limit cycle collides with the stable fixed point at the origin, and both of them disappear. Okay. Sorry, both of them don't disappear. The unstable limit cycle collides with the origin, and then the origin limit cycle disappears, but the origin becomes now an unstable fixed point. So if you were to plot the bifurcation diagram in the space of x and r, then it will look something like this. So suppose this denotes the point x equal to 0 and r equal to 0. So initially up to a particular value of r, this is r equal to 1. So up to r equal to 1, the origin was the only stable fixed point. At r equal to 1, there is a space for bifurcation like this. So the and the origin, those are the stability. So this is the fixed point C plus, and this is the fixed point C minus, which are born, and both of them are stable fixed points. Okay. Now, at some critical value of R, which we had denoted as RC, what happens is that there are, this limit cycle is born. Okay, and this fixed point continues like that. Similarly, here also there is an unstable limit cycle which is born at R equal to RC, and this continues like that. Finally, they merge together at some point over here, and they collide with, they basically this denotes the point R equal to, denotes the point R equal to RH, where the unstable limit cycle collides with the fixed points C plus and C minus, and then they become unstable. So you see that for R greater than RH, there are no stable fixed points in the system. So all fixed points are unstable. So intuitively from whatever we have seen in the 2D systems previously, that if there's an unstable fixed point and there are no stable fixed points at all, not even a saddle, then ideally the solution would go to infinity, right? It should blow up to infinity. But here it does not happen. The solution remains within a finite domain. So let us write this down for clarity. Seems that it should go to infinity, right? But it does not happen. And the reason for this not happening is that there is a volume contraction. So volume contraction occurs at every value of R. So these 2 points, they seem sort of counterintuitive, that on one hand we are saying that the solution would go to infinity, on the other hand we are saying that there should be a volume contraction. So this is what gives rise to what is called a strange attractor. Why is it called a strange attractor? Well, because it is strange, that's why. That is the short answer for it. Or it is often called a chaotic attractor when R is greater than RH. And this is where we had we see chaos, and this is where chaos had been observed for the first time. Okay. Now, when we talk about chaos, we saw that it is something which is impossible to quantify analytically because of the simple reason that the nearby solutions will never repeat. Never, there is no predictability of the system. By that, I mean that nearby initial conditions will diverge to infinity, and also there are no fixed points in the system which can give an idea of how such solutions should behave. Okay, so we can only comment on the global properties of the system or the statistical properties of the system by doing analytic calculations. So in order to visualize chaos, one must turn to computer simulations. So how computer simulations are done and how one can actually visualize chaos with the help of those sort of simulations, that is what I will show you after this. Hello. So the first thing about numerical solutions is how to discretize a differential equation. So you know that we have the equations of our system basically have a form like this, right? X to t equal to f of x. Now, how do we discretize the equation if we want to solve it numerically? So basically, this means that x at plus 2t is x at t by equal to f of x, or x at t plus dt equal to x at t plus f of x into dt. Okay, so now this basically means that if we are given an initial condition that x equal to x0, then we basically iteratively have to solve the equation for every x. We have to solve this equation for every x0 to get x1. Then we solve the right hand side for x1 to get x2, and so on. So this is what we do on a computer. So the simplest method that one can think of for solving ordinary differential equations is the Euler method, which basically says that the solution at every iteration xn plus 1 is equal to xn plus f at xn into delta t, where delta t is the size of the time step. Okay, so this is the Euler method, and this is the simplest way of solving a differential equation on a computer. But the drawback of this method is that this is only a first order method. So the errors in this equation, in the Euler method, it scales as order of delta t. Okay, so delta t is large, then the error is large, and the size of the error is of the order of delta t. So an improvement over the Euler method are the class of methods which are known as the Runge-Kutta methods or the RK methods. So the simplest RK method is the second order method, which is also known as the RK2 method commonly. So what does this do? So suppose the trajectory of your solution goes like that. You're sitting at a point xn plus n, and you want to go to a point which is xn plus 1. So the second order RK method, it takes a point somewhere in between. It calculates the solution at the in between point, and then uses this solution to approximate the total solution. So it basically tries to predict this. So we have to go from, suppose you have to go from time tn to time tn plus 1. What it, and the time step is delta t, which is tn minus 1 plus 1 minus tn. So what the second order RK method does is that it finds an approximation to the solution at time tn plus delta t by 2, and with this approximate solution it multiplies, it tries to find the final solution at the next step, which is at time tn plus 1. So the steps for solving the equation using that this method looks as follows. Okay, so first what it does is that it calculates a temporary quantity f1, which is basically um, the value of the function at time tn plus delta t by 2. And then once it finds this temporary solution, it calculates the value at x at n plus 1 as xn plus this temporary solution times delta t. Okay, so this is how the RK2 method operates. And because it is second order in time, the errors in this method are of the order of delta t square. So since delta t is usually chosen to be much less than 1, you see that the accuracy of the method is much more improved than the first order method. But usually when we have to solve chaotic systems, we need a high order of accuracy. Otherwise, there might be external artifacts in the solution which might cause them to blow up or which might make the system deviate from what it's supposed to do. So we generally use the fourth order RK method, which is also known as the RK4 method. Okay, so in RK4 method, we basically do the following. We first take the following approximations. We take f1 as the value of function f at time t, the point, sorry, so you see what we have done. Instead of approximating the solution at one point, we have made two separate approximations at the midpoint and one at the endpoint. So we get these three approximations and then we find the final solution in terms of using this equation. So this gives me the solution at n plus 1 if I know the solution at xn. And this, the accuracy of the method is of the order of delta t to the power 4. So you see that this method is very, very accurate. And of course, there are higher order methods also, but in most applications, this method is good enough. Okay, so using this, I will now show you a few demonstrations of the chaotic behavior of the Lorentz equation, whatever we had discussed in this lecture. Okay, so I guess I will stop sharing the screen and share the other screen with you now. Okay, so I'm sharing the screen now. So as you can see, I've written the code in this software called MATLAB. And here these are my Lorentz equations. So dq1 basically represents the x equation, dq2 is the y equation, and dq3 is the z equation. Okay, so I've defined the function over here, which basically is my dynamical system. So sigma and rho and beta are basically the parameters sigma, r, and beta. So rho basically is representing r, which is a real number, and beta represents the parameter b. And here I have used this function where I have tried to solve these equations using this RK4 method. So here F1, F2, and F3 and F4 are basically what I had explained a few minutes ago regarding the RK4 method. And with that, we try to solve these equations over here. So the parameters which I have chosen for demonstrating chaos in this equation are basically sigma equal to 10, beta equal to 8 by 3 or b, and the value of the r is taken as 28. So the critical value, that was RH, where the Hopf bifurcation took place, it was somewhere around 24. So as you can see, R is greater than that critical value of the Hopf bifurcation. Okay, so let us see what happens in this system. So now the dynamical variables which I have are basically contained in this array x1. If I try to plug the solutions now, you see I get this beautiful picture over here. So basically, this is my initial point. The solution starts from here and it goes around like this. And it approaches the attractor and it starts oscillating about like this. And you see there are two lobes over here. So the trajectory, it oscillates around in the slope, goes around like this. Sometimes it comes back to the slope, starts oscillating around this, and again it comes back to the slope and goes and oscillates all around and around. But if you zoom into the trajectories, you will see that they form a very dense set over here. Okay, in places they are very close to each other, in some places they are not so close to each other. And if you keep on zooming into this picture, you will see finer structures, and it appears that there is a similar repeating pattern over here. So this is what we known as a fractal, which I will come to later in this course. But let us now first try to look at the phase space portrait of these equations. So this is a typical example of a chaotic solution because as you can see, the trajectory never repeats itself. Okay, it goes round and round like that without ever repeating over itself. Similarly, we can observe the phase space in other coordinates. So what I just shown over here was the phase space in the XZ plane. Here it is, I show you a projection in the XY plane. So as you can see in XY plane, the projection looks slightly different. And in the YZ plane, it again looks somewhat like this. So the x-axis is the z-axis and the vertical axis is the y-axis. Okay. So essentially it is a three-dimensional system. So what we should ideally be doing is that we should try to visualize a whole phase space in 3D. So that is what we do now. So you see now we are able to visualize this picture in 3 dimensions. I can move this picture around for you to see. So what we saw as lobes in the earlier figure. So this is basically the visualization which we saw a few minutes earlier. This was the XZ plane. And if you try to visualize it like this, you see that this lobe is not actually a flat surface, but it is actually a curved surface, which looks like this. And similarly, this lobe is also a bit curved. Okay, this is the XZ plane. And if you turn it upside down like this, you get the XY plane. And then if you move around like that, you basically get the representation in the YZ plane. Okay. One important thing to note is that at the intersection of the two lobes, that means at this point over here, if you see the picture from this angle, you would feel that there are an infinite number of surfaces of varying curvatures at this intersection. Okay, so it seems that there is a surface which is pointing outwards from this picture over here. If you try to move this, you will see that there is another surface, and so it's basically looks like there are an infinite number of surfaces over here. Okay, so what does that physically mean? So if you remember the volume contraction thing which we had seen previously, that the volume as a function of time is a decreasing function of time, right? So if it is a decreasing function of time, then as time goes to infinity, the volume should go to zero. But we did not comment on the area. So basically what happens is that the volume does go to zero of the, by volume, I mean the volume enclosed by various initial conditions. Why? Because all the initial conditions, they start off from different positions in the phase space, and then they end up falling on this strange looking object, which is basically the strange attractor of the Lorentz equation. So at time t going to infinity, the volume of the ball of initial conditions is basically given by the volume of the strange attractor, because every point now lies inside it. All right, but the strange attractor, it looks more like a surface than a volume. That basically justifies the volume contraction hypothesis which we had seen before. Now, does this really look like a surface? That is the main question. Because over here at the intersection point, it seems that there is a bit of a volume, which, I mean, it looks more than a surface, yet less than a volume, right? So this is what we know call a fractal. So in the next lecture, when we try to calculate the dimension of this object, you will find that this object is neither a three-dimensional object, nor is it a two-dimensional object like an area. In fact, its dimension lies somewhere between 2 and 3, very close to 2. So it is close to a surface, but not quite a surface, and it's definitely not a volume. And in other words, it is a fractional dimensional surface, or it's a fractal. And you might think that fractal is something which comes out from numerically from equations, but no, fractals are more common in the real world than we can ever think of. Okay. And there is no way in which you could have got this picture of the strange attractor using analytic calculations. Therefore, computer simulations are the only way out for solving nonlinear chaotic systems. Okay, now uh, let us take a look at further details of this beautiful image over here. As you can see, the trajectory is going from this branch to this branch like that, and so on and so forth. Okay, so that there is no repeating pattern, it is more easily visualizable if we try to look at the time series of the system. So let us say that we look at the time series of any one particular variable, say the y variable. Okay, what does it look like? This is the time series of the y variable. So we start from here. There are a few oscillations over here, again some jump, again a few oscillations here, again a jump, and so on and so forth. You had seen the two lobes in the xz plane. So let us take a look at the time series in the xz plane also. Okay. So here is the time series of, sorry, yeah, right. Here is the time series of the other variable. So if you look at this, there are oscillations down here and oscillations up here. Again, there are oscillations down here. And again, there are oscillations on the positive side, negative side. And there are chaotic jumps. Basically, they do not follow any simple pattern, or they do not repeat themselves ever. Okay. And these oscillations on the negative side and the positive side basically represent the oscillations in the two lobes of the strange attractor, which we had seen before. Okay. Now, one more thing which I had mentioned while doing this, while talking about strange attractors, is that chaos is basically signified by trajectories never repeating. One thing is that the trajectories never repeat upon themselves, and the second point is that if you have two trajectories starting from very nearby initial conditions, then after a point of time, they deviate drastically from each other. And this is not the case for a periodic system where trajectories, or for a system which has a simple attractor like a fixed point or a limit cycle where the trajectories will all follow the same path after a point of time. So I have already two trajectories over here which are separated by this quantity delta. The separation, as you can see, is of the order of 10 to the power minus 14, which is a very small quantity, slightly above the machine precision over here. So let us try to look at the time series of the two variables. So this is for one variable which you had already seen. Now, how does it look for the second variable? So this is the time series of the second variable. So if you look at this plot, you will see that both the time series initially overlap completely, okay? And the overlap is very good up to a certain point, around this point. Beyond this point, the two time series, they begin to deviate drastically from each other, right? If I zoom into this point, you will see that they're overlapping over here and then they start deviating from each other. And at large times, they are not even close to each other. So this is what is known as sensitive dependence on initial conditions, and it is a characteristic of any chaotic system. So you might ask, what do the phase space trajectories, what do these trajectories look like in phase space for these two systems? So I would now plot the phase space trajectories of these two systems starting from very nearby initial conditions. Okay. Now, if you look at this, if I turn it around like that, first let us take a look at the exit plane picture. You see the trajectories, they start from here and they overlap with each other very well as they're moving along like this. They overlap with each other and they oscillate this slope while overlapping. But after a point of time, these trajectories, they begin to separate out. And then you see, although both of them covered the same volume of the attractor, I mean, they don't leave the attractor at all, yet they they are never even close to each other after at a later point of time. So this is what a chaotic system, the sensitive dependence of a chaotic system looks like in the phase space. Okay, after a point of time, although they covered the volumes of the, although they covered the sort of the region of the attractor, they remain bounded to the attractor, but they never overlap with each other. Okay, so now we were saying that chaos is possible for a certain value of a parameter which is larger than a certain critical value. So we said that the Hopf bifurcation takes place somewhere around 24. So let us see how the system would behave if we take the parameter to be below 24. So we took it to be equal to 22 over here. So first let us take a look at some two-dimensional snapshot of the phase space of the system. So you see, there is no chaos over here. What happens is that all the solutions, they converge over here at this fixed point. Okay, I can also start off with a other initial condition. So I can start off with 10. Let us see what this looks like now. You see, it starts from a different initial point, but then again, it comes and converges over here. All right. So now does the system have sensitive dependence on initial conditions? Now I can change this initial condition to say -5, 5, and 3. Let us see what happens now. You see, for this one, it goes and lands at the other fixed point. So one thing which we had seen previously was that different fixed points have different basins of attraction, right? When we had done the population of animals example. So the second trajectory which I had drawn with the different initial condition, that initial condition lay in the basin of attraction of this fixed point over here. And that is why it ultimately ended up over there. While the blue trajectory, it lied it lay in the basin of attraction of these other fixed points. Now the question is, if there are two initial conditions which lie in the basin of attraction of the same fixed point, will they go and hit the same fixed point or not? So that is the next question that we ask. And what is the answer to that? You see, I start off with a trajectory which lies in the basin of attraction of the blue fixed point now, and it converges to the fixed point. So is there any sensitive dependence on initial condition here? The answer is no. Why? Because the initial condition of the yellow and the blue trajectories are very different from each other. Yet as time progresses to infinity, they all converge at this fixed point over here. All right. So when the system becomes non-chaotic, then there is no sensitive dependence on initial conditions. Depending upon its basin of attraction, all initial conditions in a given basin of attraction will be attracted to the same fixed point or the same limit cycle. Okay, so we have now seen that with the help of computer simulations, one can actually get insights into how chaotic systems look like. And we have also seen that how chaotic systems are characterized by a sensitive dependence on initial conditions, and they can have a strange attractor. By a strange attractor, I mean that the volume of attractor is not a integer dimensional, or I'm sorry, the dimensionality of the attractor, it is not an integer. That means the attractor is not a two-dimensional object or a three-dimensional object. Rather, its dimension appears to lie somewhere between 2 and 3, and therefore it is a fractal. So in the upcoming lectures, we will focus on these two issues in more detail. Okay, we'll focus on how to quantify the sensitive dependence on initial conditions using certain quantities which are known as Lyapunov exponents. And we'll also see, given a fractal object, given an object with a fractional dimension, how can we extract what the dimension of the object is? Okay, how to quantify fractals basically. And then we will study about the applications of fractals in various real world systems. Okay, so that's it for today.